So I have started recording, and yes, here is my periodic table. Okay, let me see. Yes, this is better. Okay. So what do we know about periodic table here? First of all, what is this first group? What do you know about this group?
It is a group of alkali metals.
Okay. So why do we call it alkali metals? Why do we call them that way? Any idea? Why do we call them alkali metals? Any idea? Abdul Wadood, you are in grade 8, right?
It's because they are all reactive metals.
No, but why alkali? Yusra, are you in grade 8?
Miss, can I answer?
Yes, Sarah.
Miss, it's because they only have one electron, and so it's very, very easy to give it away.
No, my question is, why are they called alkali metals? They are called alkali metals, right? Group 2 is called alkaline earth metals.
Ma'am, I'm sorry, mic problem I had. Ma'am, because they are reactive when they are in water. They react with water to form alkalis.
Thank you very much. Yes, that was the answer I was waiting for. That they are called alkali metals is because they react with water to give you an alkaline solution. So that is why they have been named as alkali metals. Okay, so this is group 1, group 2, and then what are these? They are
Transition metals.
Transition metals.
Transition metals.
Yes, so this is transition metal, and then this is group 3, and then this is group 4, group 4. Okay, so where do we have so from where do we get the non-metals? From where do we start getting the non-metals? Where is that boundary? Where is that boundary between metals and non-metals? Where do the metals stop and non-metals start?
From boron, silicon.
From
Very
and
good.
there's like
Yes.
a staircase going down.
Yes. So help me make that staircase if I am not mistaken.
No, under silicon.
Under silicon.
Oh, under silicon, and then this.
Yeah, and germanium is also included in it, but it comes under the staircase.
Yes, okay, let me see the staircase. I always tend to forget it. You know, knowing the periodic table is very important. Arsenic, and so it's this way. Tellurium, and then astatine, and then this. Now, these are metalloids. These are metalloids. What do I mean when I call them metalloids?
Semi-metal.
Semi-metal?
They have properties of metals and non-metals.
Yeah, under certain conditions, they behave as metals, and at other conditions, they behave as non-metals. So it depends upon the conditions you provide to these to these substances. Okay, so they will behave accordingly. And so on the right side of this staircase, we have all non-metals. These are all non-metals, and these are all metals. On the left hand side, we have all the metals, and we will not deal with these. These are artificial. Okay, so we will only deal with these. Okay, so okay, so now let's get started from group 1. What do you know about group 1? So they are highly reactive, somebody said, and that is because they have to give away only one electron to be stable, right? And so it's easier for them to react. Okay, because for example, let's draw lithium because it's easier to draw. So the mass is 7, proton number is 3, so that means 3 protons, and neutrons must be 4. Okay, and if the protons are 3, then electrons also must be 3. And so this is the rough atomic structure. And so it is easier to lose the outermost and get the stable structure, and therefore that makes this really reactive, right? Okay, so keeping this point in mind, what do you think? Which one will be more reactive of group 1 and group 2, and why? Which will be more reactive, group 1 metals or group 2, and why? Yes, Aisha?
Group
Group
1
one.
because they have one electron and it's easier to lose that one electron.
Yes. So group 2 metals will need to lose 2 electrons, which is more energy requiring, because losing an electron also requires energy. And so it will be more difficult to lose 2 electrons as compared to 1 electron. So definitely group 1 elements are going to be more reactive than group 2. Okay, my second question, keeping this point in mind, how do you think the reactivity would trend down the group? Will it increase or will it decrease, and why?
It will
Zainab?
increase.
Why?
Lithium will be the least reactive in the group.
Why, beta? Why? Okay, whenever you answer my questions, please do not just state the answer. I want to hear the why. Without why, there is no answer. Yes, Zainab, come on, tell me the reason. You said reactivity will increase down the group. You are right, but please also tell me the reason.
I don't know.
No, I'm
Miss,
giving
can
you
I
a
answer?
Can I
no. I want Zainab to think. See, I'm giving you a hint. We just discussed that the reactivity depends upon this outermost electron being lost, right? So now, keeping this in mind, what do you think is happening? What's happening down the group? What's happening? Okay, I am just making the nucleus and the outermost shell. Okay, I'm skipping the inner shells because they do not participate, so I'm just skipping them. Okay, for example, this is lithium, outermost shell only. I'm only making the outermost shell. This is sodium, bigger, because 1, 2, 3. This must have 3 shells. Okay, then this is 1, 2, 3, 4. Please keep yourself muted. 1, 2, 3, 4, 5. So what's happening?
The number of shells are increasing.
Yes, okay. And what else? So they all are losing the electron to react, this outermost electron, and they all have 1 electron in their outermost shell, and they all are losing in order to react because they cannot gain. Okay, they have to lose in order to gain stability. Now my question is, do you think that it will be easier, it is getting easier for them to lose this outermost electron, or is it getting more difficult?
It is getting easier for them because they also have the second last shell, which is stable.
can I tell?
Okay, yes, okay, Yusra.
As we're going down the group, the reactivity is also increasing because the number of shells are also increasing.
So how is that affecting?
Ma'am,
Because the nucleus, there's more distance from the proton, like from the nucleus to the.
Yes, you're right. Yes. The
So there will be less attraction, and so it will be easy to remove the electron.
Yes,
so it will be.
Yes. So the distance between the outermost electron and the nucleus is increasing as we're down the group. Can you also see that the atomic radius is increasing? The atomic size is increasing as the number of shells is increasing. Another thing, these shells are filled with electrons. They are all filled up shells. So they have a lot of electrons, and you know electrons are similarly charged. They all are negatively charged, and so they will repel. The more they will repel. So there is, a competition going on between two forces, attractive force between the electron and the protons inside the nucleus, as well as there is some repulsion going on between these electrons, amongst each other. So the more the electrons there are, the more this repulsive force will increase. And so, and it will be easier for the outermost electron to be lost. Okay. I felt, okay, let me ask this question. Let me see how many of you know this answer. What are these shells? What are these shells? Are they rings around the nucleus? Yes, Aisha?
No, they are like
They're imaginary pathways for the electrons.
That's a good answer. That's a good answer. Anybody, any other addition? Any other way of thinking
yes,
about them? Yes?
yes. They are also like we can imagine them as the layers of atmosphere. For example, on Earth, there is one layer of atmosphere, and then there is another.
No, beta. At layer of atmospheres are physical structures. They are made up also. These are not physical structures. They are not physical structures. Yes, Javeria? Yes, Javeria?
They are energy levels.
Very good. Very good. What do you mean by that?
That I mean that um I mean by that before the as we go further away from the nucleus,
Yes,
energy decreases.
I cannot hear you.
As we go farther away from the nucleus,
Yes,
the energy decreases.
no.
The force pulling them.
As we are going away from the nucleus, the energy is decreasing. Sorry, the energy is increasing.
Yes, that's
No. The energy is increasing. Okay. Yes, Abdul Wadud?
Yes, ma'am, I had the same answer. I was about to send the same answer.
Yes, okay, so this is correct. This answer is correct. Okay, I just want you to add something to it and understand it in a better way. I told you this has to do with electrons are resisting this pull which is exerted by the protons within the nucleus. Okay, the protons within the nucleus are trying to attract the negatively charged electrons, right? And so more the energy the electrons have, the better they can resist this pull. Okay, therefore the electrons which are in the innermost shell, they have the least energy, and therefore they cannot resist this pull too well, and so they land up in the innermost shell. And so the electrons which are in the outermost shells, they have more energy to resist this pull. Okay, so these electrons which are in the outermost shell, they have the most energy, which also helps them to move away, to get out of the the atomic space. They leave. They have so much energy that they can leave. So remember, the energy is increasing. And I also gave this analogy of kids. Think of these electrons as kids, and this is the mother. So the younger the kids are, the closer they cling to the mother. As kids get older, they get more independent, and they can go away. They can stay without the mother for longer, right? So remember it this way. Okay, so that's what I was trying to explain, is that the outermost electrons, as they get farther away, because there are so many electrons in the way, I did not make all the electrons, but of course all these shells are filled with electrons. They're fully occupied by electrons, and so there are repulsive forces, because of which it is easier for these outermost electrons to be lost as we go down the group. Okay, so the reactivity increases down the group, both for group 1 as well as for group 2, because again these are metals. Okay, what do we understand when we say metal? This is a metal. In chemistry language, what do we understand by metal? Yes, Aisha?
It conducts electricity and heat.
Well, yes, that is one of the characteristic features of metals, but what makes,
It's also hard,
okay, but
but that's not
mercury,
always true.
yeah, there are
They
exceptions.
have shiny appearance.
Sorry?
They are malleable and ductile.
They are shiny. They look
Okay,
shiny.
these are all physical features that you guys are talking about.
Ma'am, they form positive ions.
They
Yes,
are good conductor of
yes,
heat and electricity.
yes, Abdul Wadood's answer is correct. You know, all these features that you guys have mentioned, they are also correct, but these are physical characteristics. These are physical features. What I wanted to ask is, for example, mercury. Mercury is not hard. It is not, you know, all those things that you just said, malleable and this and that, but it is still a metal. So what made scientists categorize it as a metal?
It
Metals,
forms positive ion.
yeah, another way of saying it is they lose electrons. Anything that lose electrons is a metal. Do you understand? And which is the same way as saying that they form positive ions, because when they will lose electrons, they will form positive ions. Same thing. So a neutral metal, when it loses electrons and forms a positively charged cation, this is a metal. Any substance doing this is a metal. Remember this. Why did we say that substances, these all are metals, these are non-metals, is because they can give away electrons. That's why they are metals. They accept electrons. That's why they are non-metals. And so the definition of non-metal would be just the opposite. Substances that accept electron to form the anion, those substances are non-metals. Okay, so understand that. So losing one electron, alkali metals. Losing two electrons, alkaline earth metals. Now you might ask, why are they called alkaline earth metals? Maybe because they are found in the earth. I don't know. I don't know the answer to that. But well, that's a good question. You can ask, you can, you know, search and find out. Then these are transition metals. So what makes transition metals different from these two? Yes. Yes, Yusra.
They form a colored compound.
Again, the okay. And how else are they different? Yes, Aisha?
They form different ions. They can either lose one or two or multiple numbers.
Yes. So how will you say that? You will say they have
Different
very,
charges.
yeah, they have variable oxidation states. Okay. Or yeah. Okay. Or if you want to, yeah, that's a good way. That's the standard way of saying that they have variable oxidation state. I would not want you to say this any other way. But at your level, when you have not done oxidation state, you will say, no, what's this oxidation state? So for you, I would just say that, you know, one transition metal can have different charges. One transition metal ion can have different charge or more than one charge. Okay, it can exist as ions with different charges. Okay, this is the second best, but you know, variable oxidation state, that's the best way of saying this same thing. Any other difference? So they form colored, they form colored compounds, they have variable oxidation state. Is there anything else? Think. Is there any other difference?
We have a shiny surface.
Yeah, they have shiny surface too. 1 and 2 also have shiny surface. Anything else?
They are malleable and ductile.
They're hard.
Yes, they are harder.
Their boiling point.
Yeah, these transition metals are harder. They're very, very hard. See, you must have heard of, you know, things made up of copper, zinc, cobalt, iron, right? We have chromium and steel. Okay, but have you ever
Yes,
heard, have you ever heard of, you know, solid things made up of sodium? But this is a metal, but why don't we use it for making anything?
Because they're soft.
Right, they're soft. They're so soft you can cut them with knives. And I was just searching for a video to show you guys.
And it is reactive, more reactive.
Yes, and then they are reactive. Yes, and they are soft. And so that's why that's another thing that differentiates them from transition metals. They are like hard. We can use them for making aircrafts, for making other things. Okay, you know, like buildings and all those construction material, because they are hard. Okay, they have strength. Okay, so we talked about the reactivity series. We talked about the reactivity increasing down the groove. Okay, so how do we in the lab show this increase in reactivity? In the lab, how do we show this increase in reactivity? Easiest way. Yes, Abiha?
By reacting it with water.
Very good, Abdul Wadud. Very good. I would like it a lot if you please raise your hand and then answer, because you see then others who are raising their hands, they will not like it. Okay, then they will also stop raising their hands, will just immediately unmute themselves. Okay, so yes, you are right, Abdul Wadud, that we can use water. Okay, so how is the reaction varying as we go down the group with water? What is the pattern? Yes, Aisha?
The more reactive ones might release hydrogen, and the less reactive might not. They might just, like that, make an alkaline solution.
See, all of them are reacting with water. First of all of them are reacting with water to form alkali. And okay, what's let's discuss the equation first. Okay, let's discuss the equation first. For example, let's take lithium. Okay, lithium, solid. This is in atomic neutral stable, I mean neutral state. Okay, no, this is not an ion here. Understand this. This is natural atom. Okay, this is not an ion reacting with water to form. Now I'm gonna open this up to make you realize what's happening. So this is H2O, right? This is H2O. Okay, this will react as, this will break up here. So this will come off as hydrogen ion, and this will come off as hydroxide ion. Okay, now because this is a metal, all it knows is how to lose the outermost electron. It cannot do anything else. Okay, so this will lose its electron and will become a cation. When it becomes a cation, it will definitely be attracted towards this anion. Of course, it cannot, two cations cannot react with each other. Stop playing with the emojis, please. Okay, so this is cation, these are anions. Okay, lithium hydroxide plus hydrogen ions. Two hydrogen ions will combine to form the hydrogen gas. Okay, this is in the aqueous state. This is liquid state. This is how the reaction is. Okay, is it balanced? This is not balanced, right? So how can we balance it? We have one lithium here, one lithium here, two hydrogen here, three hydrogen here. So let me add two here. That makes two oxygen here. And so I'll add two here. And so now I have two hydrogen here. Sorry, four hydrogen here, and then four here as well. 2 plus 2, 2 oxygen here, 2 oxygen here, and then 2 lithium here. Okay, so now this is balanced. Okay, so this is how the equation of alkali metals with water look like. All the alkali metals will have the same equation. Okay, only the symbol will vary according to, for example, sodium. For example, sodium with water giving us sodium hydroxide plus hydrogen. Again, 2, 2, 2. So only the symbol for the metal would change. The rest of the equation will stay the same. All of them will undergo the same reaction, but they will only differ in the readiness with which this happens. As you go down, the readiness of this reaction increases. So how do we know this? I mean, how in a laboratory, when you will carry this reaction out, how can you observe it? What will be your observation? How will you know that this is more reactive than that? Yes, Yusra? Yes, Yusra?
Miss, I wanted to ask you a question.
Okay. Yes.
Miss, I wanted to ask you that in the book it says that except like from the alkali metals, except for lithium, if we react any other metal with water, they're going to melt. So how can we do this with sodium and water?
Yeah, so yeah, they melt. I'm going to show you a video. Yeah, they melt. Why do they melt? Do you know? Yes, Abdul Wadud? Why do they melt? Zainab?
Miss, before you ask the question before this one, I raised hand for that one.
Okay, okay. Answer that question.
The most active one would explode as soon as we put it in the water.
Very good. Yes, good. And see, yes, very good. So your thinking is good. So our observations will vary. This is going to be explosive. Really, really. This is so explosive, by the way. We don't have francium. This is very unstable. Highly, highly unstable. Its half-life is, we remember radioactivity. It's highly radioactive. Its half-life is really small. We have only very few atoms of this francium. So forget this. And I think cesium is also not easily available. Yeah. Yeah. So this is also very unstable. So yeah, I think from rubidium onwards, we can show in the laboratory. And they have videos on YouTube and they're really interesting. I enjoy watching them. You can also go ahead, write down reactions of group 1 metals with water. And it's really fun. So when you add rubidium in cold water, so how many energies? Sound energy, you will hear hissing sounds, and then you will see gas bubbling, okay? And what else? You will see a steam coming out. What is that steam, by the way? And you will also, if you touch and don't touch, okay? By the way, these metals, do you know these metals are banned to be used in school labs because their reaction with water is so explosive, it can cause accidents. So I
Ma'am,
would,
I've seen
Yes, we've done it in class in
sodium.
the science
Yes,
lab.
I've seen sodium reacting with water.
Yes.
yeah, and you have to do it very carefully, okay? Only teachers are allowed, and in foreign countries, these metals are banned from school labs, okay? Because of the accidents that have happened there, they have banned it, okay? So yeah, you got to be careful. And they, even if you keep them open in the air, they react. They're so reactive that they react with the oxygen and moisture in the air, okay? And so
yes, Miss.
yeah,
Miss, if it's stored under oil, why don't they react with it?
why don't they react with oil?
Yeah.
You answer that question. That's a very good question. You answer, try to answer. Think.
Is oil not reactive?
But oil is used as a fuel, right? So
Oil is not so.
the oil is used as a fuel. If it wasn't reactive, how come we use it as a fuel? Huh? Does it have to do anything? How are metals different from oil? Metals form ions, they form salts, right? And oil are covalent. They are covalent simple molecules. They may be big molecules or small molecules, but they are simple molecules, okay? And these form ions. So maybe it has to do with that. Remember, polar and non-polar, they don't go along, they don't react. Remember that thing? See, water does not dissolve in, oil does not dissolve in water. Why? Same thing. Water is polar and oil is non-polar. So they don't go along. They stay there together without mixing. They separate, okay? Same is the case here. So because this needs an ion to react with, it has to give an electron. Oil is not going to do that. Oil is not accepting any electron from these metals. So metals cannot react with oil. Okay. Yes, if the metal is exposed to air, now air has a very reactive gas, oxygen, and also water vapors. So water is a polar molecule. Can you see? It reacts with water so vigorously. Another thing I wanted to, that's very important, is that these reactions are spontaneous. Spontaneous meaning you don't need to heat for this reaction to take place. You just introduce a lump of sodium in water and you see what happens. And you just watch the show. But the thing is, we don't heat it. So these reactions that take place on their own without you helping it in any way, like without stirring, without heating, these are called spontaneous reactions, and they are usually exothermic. Exothermic meaning releasing energy. You know exothermic, right? Grade 8 students, do you guys know exothermic? What is
Yes.
exothermic? Yes, what is exothermic?
I do, sir. I do, miss.
Yes. Yeah,
Is
Nabil,
it, is the
you're grade 9 student, you would know. Yes, okay.
yes, miss. The reactions producing heat?
Very good. Reactions that release energy in the form of heat, thermal energy, they are called exothermic. So they are exothermic, right? They are so, and now Zainab, oh sorry, Yusra, your question. Are you here? You said, why do the metals melt, right? Where is Yusra? Yes, okay.
I'm here, miss.
Yes. So your question was, why do metals melt? It is because so much thermal energy, so much heat is being released. It's enough to melt them. It's enough to melt them. Now you will be amazed. Wow, this is a metal and it's melting just by the energy released by a reaction. So that means the melting point must be low, right? Melting point of these metals must be low. Okay, so let's talk about their melting point. First of all, tell me, what decides a melting point of a substance? What factor decides the melting point of a substance? Yes, Aisha?
Its electronic structure.
Nuh-uh. Come on, I have discussed this in my previous classes. Remember physical properties, chemical properties, and I said whenever they ask you whenever they ask you a question regarding physical properties, what should you look at?
And the intermolecular forces.
Very good, Abdul Wadud. How did you know that?
I just remembered.
Good, good. I want you guys to remember it this way. Yes. So physical properties have to do with the intermolecular forces. You know, these forces intramolecular between the molecules. Okay. And then you have chemical properties depend upon intra meaning within, inside the molecule. So chemical reactions, they depend upon these intramolecular bonds, and physical properties depend upon intermolecular forces. Okay. Inter meaning between. I'm just using shorthand. Intra meaning within. Okay, so melting point is a physical property. So we will talk about intermolecular forces. So now tell me, So melting point is low. What does that mean? So, okay, can anybody tell me the structure of metals? What is the structure of metals? How do they exist? If you have a lump of, for example, sodium, can you draw its structure, atomic structure? How will you draw it? How do they exist? Come on, grade 8 and 9. Nabil, I want you to answer. Grade 9 students. You should know. Metallic structure, come on. Okay, Aisha?
It would be like a solid with tightly packed atoms, but the electrons would be free moving, delocalized electrons.
Very good. Yes. Another way of saying it is these are cations embedded in a sea of electrons. So I will draw them like this. Okay, by the way, they ask you to draw, so you should know how to draw. These are cations meaning that they have lost their outermost electron. So I will put a positive charge. So for example, if this is sodium, because they are in group 1, therefore they will lose only 1 electron, and so their electrons are roaming around here and there. So 1 2 3 4 5 6 7 8 9, so there should be 9 electrons because 1 electron from each atom. So let me make 1 2 3 4 5 6 7 8 9, and they are delocalized, meaning they are free to move within this space. That's why they conduct electricity. That's why they conduct electricity. Why? Because they have these mobilized electrons. They have these mobile electrons delocalized. What does the word delocalized mean? Delocalized mean that these electrons are not confined to any one atom or when any one ion, but they are free to move within this space. And I give this analogy of, mothers who have come to a park with their kids. They sit down together to have a meal and the kids are playing around, but they are only allowed to play within the park. Okay, so if you look at them, you cannot make out which kid is whose, which mothers, right? But they are still there with their mothers. Whenever the mother wants, she can call the kid and the kid will come up to her. But just by looking at them, you cannot make out which kid is which mother's. Did you understand? So in the same way, we cannot make out which electron belongs to which cation, but they are free to move within this space, and that's what makes them a good conductor. So this is their structure. Okay, this is called a metallic structure, and this is metallic bonding. Okay, now melting point. So melting point has to do with the attraction between these cations, the positive charge of this cation and the negative charge of this delocalized cloud of electrons. The greater the charges, meaning, for example, if we talk about group 2 metals, such as, let's talk about calcium, for example. Now, calcium, each cation will have 2 plus, okay? And so 9 more electrons. So what do you expect? The attraction will be greater because there is greater charge, okay? More the charge, more stronger the attraction, right? And therefore higher the melting point. Because what are you trying to do when you're melting? You are trying to break this so that they come into the liquid state, right? You are trying to break these forces so that they exist this way, random, this is the melted state, right? So in order to get them from this arrangement to this arrangement, you have to break these forces of attraction. And more the charges, more the magnitude of the charges, stronger the attraction, more energy required to break these into these, right? So therefore, the melting point, what do you think would be happening to the melting point as we go down the group?
Ma'am, the melting point would increase.
The missing increases.
It would
See,
decrease.
It decreases, miss.
see, when we are going down, what's happening? When we are going down a group, wait, here. This is how the atomic radius is increasing, right? So what's happening? So this will turn into a positively charged cation and there will be delocalized sea of electrons, right? So as the radius increases, because now the radius is bigger, and so the attraction would decrease, think of this. So for example, this was this, okay? Now if I draw for cesium, for example, if I draw a diagram for cesium, there will be bigger radii, okay? And so same number of electrons. The number of electrons is the same, but the distance is increasing between the outermost, the delocalized sea of electrons and this. Did you understand this? And so
Yes, ma'am.
therefore,
So it would decrease.
yes. And so this electrostatic attraction gets weaker. And so you need less energy to melt them. And therefore the melting point decreases as we go down the group. But what would happen to the melting point as we go across a period? Yeah, it should increase.
Yes.
Because remember, this point, they're losing more electrons. This one is losing 3 electrons per atom. This is group 3, remember? So this is losing 3 electrons. So the electrostatic attraction is going to be stronger and therefore higher melting point. So melting point increases this way. Now, when we talk about non-metals, the story gets different. Okay, I will not get into that for now. So here you understand that the melting point is decreasing both for group 1 as well as for group 2. Okay.
And even the boiling point, it also decreases.
Yes, yes. So same thing, boiling and melting, you have to look at these electrostatic attraction, okay? The inter-atomic. Here you don't have molecules, you have atoms. So we'll call them intra-atomic forces of attraction. And same goes for group 3 as well. The melting and boiling point should decrease in group 3 as well. Okay, what about the density? What about
Miss, it decreases.
Increases.
Okay,
It increases.
whatever you're saying, decrease or increase, please support it with your reasoning. Support it with your reasoning.
Miss,
As
I
we
don't
go
get
down
the point,
the
like how the melting point is decreasing and increasing one.
Yes, Heba, what did you not understand?
No, miss, it's me. I don't get how, like, you know that the melting point is increasing and decreasing.
Okay, beta, I told the whole story.
Miss, just a review.
Uh,
I'll get it.
see, what I said was that,
And can I tell
yes,
the
okay,
density?
yes, okay. For example, we are comparing these two. Yes, Abdul Wadud, go ahead, explain.
Ma'am, as the uh, atomic radius increases, the
Yes.
density also increases.
Beta, right now, Zainab is asking melting point. Can you recap real quick, summarize it? Comparing these two structures, or should I do it?
Ma'am, you can explain better.
Can
Okay.
I?
Can
Yes.
I explain?
Yes, Aisha.
When the radius becomes bigger, then there's more distance between the protons and the electrons, so the intermolecular.
Or you can say
Uh,
between the nuclei of each and the outermost electrons, the sea of electrons. Yes, Aisha, very, very good. Yes.
So there is less attraction, and so it's easier to break the intermolecular forces.
Yeah, very good. Yes, intermolecular, or you can call intra-atomic forces of attraction here. Did you understand, Zainab?
Miss, so what happens if it is easily breakable?
So then that means we need less energy to separate them, because in melting, what's happening? We are disrupting this regular arrangement into this irregular, because you know the difference between solid and liquid, right?
Yes, miss.
Yes. So in order to get the solid arrangement into liquid arrangement, we need to break these forces of attraction, because these forces of attraction are what keeping them in this particular solid arrangement. So we need to break them. Okay. So the energy required to break these forces of attraction is less, because these forces of attraction get weaker as the radii or the radius of each atom is increasing. That means the positively charged protons in the nuclei are getting farther away from the delocalized sea of electrons.
Oh, so miss, you mean that when the atomic radius increases, the energy needed to melt decreases?
Yes.
Got it, miss.
Okay. What about density? Keeping the same thing in mind. Think
Yes,
about
ma'am.
density.
It also increases as
Increases.
the atomic radius increases.
Okay, what is density first of all? What is density? Definition?
Mass per unit volume.
Mass over volume.
Very good. Mass per unit volume. Now, keeping this formula in mind and this arrangement, tell me what's happening to mass per volume? And let me give you a hint. Let me give you a hint. If you remember the atomic structure, when you did the atomic structure, that was the one of the first things you guys did when you started studying the science subjects. Remember, more than 80%, in fact, do you know that one atom is like a football court with the nucleus as the football at the center of the court? Do you know how big a football stadium is?
Yes, ma'am.
You all watch
Yes.
matches, right? You all watch matches. You know and you realize how big that ground is. And can you compare the size of the football with that ground? You know the difference, right? So
Yes.
Yes, miss.
this nucleus is like a football in the center of that football stadium. That's the analogy they have used in the books. Now, as the radius is increasing, what's happening? There 90% of this is empty space with only clouds of electrons, and electrons have negligible mass. We don't even count it. When we count the mass of an atom, we only add the protons and neutrons. We don't add electrons because their mass is negligible. So they are filled up with electrons, but the electrons have negligible mass. Most of the mass is concentrated within this central nucleus. Now, what's happening to the number of nuclei per unit volume as we are going down the group?
Ma'am, it increases.
Miss, is it?
Yes, it decreases. Why? Because the radius is increasing. So it's the same volume can accommodate less number of atoms now. You understand? And so, no. Sorry. No.
I'm saying it increases.
Yeah. So, so the thing is that the mass is concentrated within the nuclei, right? And nucleus is small. You can have, I mean, the radius is increasing. Yes, I understand. You will be confused that, the radius is increasing, so there should be less atoms accommodating with per unit volume. But the thing is, yes, the radius is increasing, but remember, the number of nuclei, can you see the way the mass is increasing as you go down the group? How is it increasing? Look at this. The mass is 7, 23, 39, 85, 133, and I don't have the mass of
Is
Frank.
it because the number of
So
electrons?
mass is, okay, wait. So the mass per unit, the atomic mass is increasing down the group, okay? So you have, because nuclei occupies less space. As I told you, it's like a football at the center of the football stadium. So nuclei are smaller compared to the whole radius. So more nuclei can accommodate, and so the mass per unit volume is increasing down the group. Okay, so the density increases. Am I right? Yes. The density of the metals tends to increase down the group. Okay, and the way I explain it is that, you know, the nuclei, the mass is in the nuclei. And so the nuclei, and you can see that the increase is very drastic. So they can manage to squeeze within a small volume, and the mass is concentrated in the nuclei. So you can have more nuclei in the same volume. So you have greater mass per unit volume. Okay, so yes, I understand that the radii are increasing, but they are only clouds of electrons. The nuclei are squeezed within a small volume, and within the same volume, there's more mass, so density increases. Okay, so I will say mass, atomic mass is increasing per unit volume, and so density is also increasing. Yes, Yusra?
No, miss, it was just by mistake.
Okay, Muhammad? Okay, so density increases down the group, okay, melting point decreases down the group, okay, reactivity is increasing. Now, in turn, what I wanted to mention about reactivity is that, as you mentioned, lithium is the, can you please? Lithium is the only one that, that reacts steadily, and then the rest of them, they react strongly, and so much so that they, you know, we have other observations. Okay. Reaction with, so this, there is this table, reaction with water and reaction with air. What does this mean? Air means oxygen. Okay, air is just other common term for oxygen. Okay, what does tarnish mean? What does the word tarnish mean? Any idea?
Smooth?
Smooth? No. What does the word tarnish mean?
Ma'am, to the exposure to air?
No. No.
Rust.
Who said rust? You're close. You're close. Who said rust?
Miss, become less valuable.
Ma'am, corrosion?
Discolor.
Ma'am, corrosion?
Yeah,
Dull.
yeah, Google search. Google search and then tell me. See, the tarnish is reaction of metal with oxygen. Okay. Okay, I'll try to show you a video, okay, after this. I am not sure if I have it, but okay. So yes, it is similar to rusting. Whoever said rusting, it is similar to rusting. Rusting, the word rusting is confined to, it is only used for iron. Okay, this is used for iron. For rest of all the metals that react with oxygen, we use the word tarnish, which includes copper, aluminum, and what other metals might react with oxygen in the air. We use the term tarnish, rusting, but the reaction is the same. The only difference is of metal. Rusting is used for iron. For all the rest of the metals, we use the word tarnish. Okay. For example, okay, let me write down the equation for iron reacting with oxygen to form iron oxide. Okay, which is red brown in color, because of which you see that red brown. And so 2 3s are 6, 3 2s are 6, and 2 2s are 4. So this is the equation, okay, for rusting. And if you have similar equation for, let's suppose I write about
Sodium.
Yeah, okay. Sodium reacting with oxygen, forming sodium oxide. Okay, because oxygen is -2, so we will write 2 here, and sodium is +1, and so 1 we don't write. Okay, so now if I balance this, 2, okay, 2 2s are 4. So it is something like this. Yes. Okay, so I will call this rusting. This is called rusting, but this is called tarnish. Okay, so this sodium is highly shiny metal, but this is like dull gray dull. This is gray or black, maybe, you know, dull color. So if you have a lump of sodium, if you have seen in the school lab, and maybe if your teacher has shown you the reaction of sodium with water, you might have seen the lump of sodium. If you have, I'll show you a video. It has a gray dull surface, but when you cut it, the cut surface is pure sodium which has not reacted yet, and so it is very shiny and fresh. It has a fresh shiny look. This is gray black dull. Why? Because it's not pure sodium, it's sodium oxide. It's a compound of sodium which is gray black in color. Okay, and that is why the metals, they lose their luster with time. Why? Because the surface metallic atoms, they have reacted with oxygen to form this oxide, which is gray, black, or, you know, color. Aluminium undergoes similar reaction. Aluminium reacts with oxygen to form aluminium oxide. Please keep yourself muted. Okay, and raise your hand if you want to say something. Okay, the thing is, this rusting, another difference between the two is that rusting keeps on going. I mean, until all the iron has reacted with oxygen. It continues until all the iron has rusted. Whereas this tarnish of other metals, it is self-limiting. Self-limiting meaning when the surface atoms have reacted with the oxygen in the air to form the oxide, they form a protective layer. For example, if this is the lump of sodium, these surface metals will react with the oxygen of the air in the atmosphere, and they will form an oxide layer which will protect the inner metal. Okay, this is another difference. Rusting does not do that. Rusting does not make that protective layer, whereas these oxides of other metals, which are, you know, the reaction which is called tarnish, this is self-limiting. It forms a protective oxide layer, and that is one of the reasons why we use aluminium, because it reacts with oxygen of the atmosphere to form this protective oxide layer, which protects the innermost metal, and therefore the rest of the metal does not tarnish. Okay. Okay, so this is what we mean by tarnish, is basically reaction of the metal with the atmospheric oxygen. Okay, so as the reactivity increases down the group, same is the case with tarnishing. So the tarnishing will increase as you go down the group. Okay, yes, Abdul Wadud?
Ma'am, the rust occurs when the iron has water on it only. Otherwise, the rust doesn't occur. Why does that happen?
Okay, that we will discuss when we'll do the transition metals. Okay, I just mentioned iron so as to differentiate it from rusting. Okay, the rate of reaction is increased by moisture of rusting, but even without moisture, the reaction does take place, but it is too slow. It is too slow, okay, for us to observe. It takes years and years, but if there is moisture, the rate of reaction is fastened. Okay, it accelerates. Okay, so if you don't have any question, the last thing is that so we saw that when metal reacts with water, we have oxygen gas produced, right? This oxygen gas is produced. Now this oxygen gas then burns with the metal. I mean the metal, because you know that there's a heat, because this is a highly exothermic reaction, heat is being released. So that heat also causes, or if you are heating, that will cause the metal to burn with the hydrogen, and that causes a color, characteristic color, flame test, a characteristic color. Uh, that's when the metal either burns the hydrogen, or the metal reacts with the oxygen directly as well. It gives a flame, characteristic color of the flame. Okay, those flame colors are used as diagnostic tests for metals. Okay, and you will have to learn the colors. You will
Miss,
have to learn the colors. They are asked in the exams and in alternative to practicals, ATP. They're very important. So and you know, you will have to learn them. Either you come up with a mnemonic or devise some method, but you'll have to learn them. So lithium gives us red flame color, sodium gives us yellow color, potassium gives us lilac color. So it is basically the ions that react with the oxygen, or they burn somehow in fire and flame, okay, or due to the, you know, heat which is released from reaction. Please keep yourself muted. That's when you get the flame color. Yes, Sabiha, you wanted to ask?
Teacher, what is lilac?
Lilac is a color. I think it is somewhat purple. Not exactly, but yeah, somewhat purple. I'm not sure though. Yes, Abdul Wadud, you have a question?
Ma'am,
Okay,
can you
teacher.
just brief on like ionic bonding and covalent bonding? Because I have a test tomorrow.
Beta, you tell me. You tell me. You tell me what is the difference between ionic bonding and covalent? Who wants to help Abdul Wadud out? Yes, Aisha.
Miss,
Ionic bonding is when a metal loses an electron and a non-metal gains that electron. They
Very good.
both form ions, and because of the opposite charges, they attract to form a bond.
Very good. Very good, Aisha. And
And
covalent is?
covalent bonding is when two nonmetals share electrons and they form a bond.
Right, because they both want to gain. So we don't have an electron donor here. In case of covalent, both are electron acceptors. So they both want to gain electron. And so what they do is that they share.
They
So
can also form a single bond, double bond, and triple bond.
yes, that's usually in hydrocarbons. That's usually when you're dealing with carbon. Okay, Zainab, I saw your hand raised. Do you have a question? Okay.
Miss, I was just asking that when you were explaining the reaction with lithium with water, but you told that it produces oxygen. And in the paper you wrote it produces hydrogen.
No. I never said it produces oxygen. I said metals react with oxygen in the air.
Oh, okay, miss.
Yeah. Okay, now I'm sharing my screen. I want to show you this video. Can you guys see my screen?
It's just loading.
Yes, miss, I can see. Yes, miss.
Okay.
Yes, ma'am.
Now, I didn't get much time to explore through the best video. So whatever I have, I'm just showing that. Okay. So this guy is cutting lithium, sodium, and I don't know what the third metal is. So I want you to see how soft they are, how he's cutting. Okay. And then he will be showing you the cut surface, the other surface. So the surface will be, you know, the dull black because of tarnishing. But when you'll see the fresh cut surface, that will be, you know, shiny and fresh. And also then he will add each metal into water, and I want you to observe the differences. So lithium will be least reactive of all, and then you will see, you know, a more increasing explosion. Okay, and then, you know, after this class, go ahead and explore yourself. There are many videos out there. Okay, I'm playing.
I've got a piece of sodium here, pretty easy to cut. You notice when I cut through that the fresh sodium is very shiny compared to the rest. Zoom in real quick and see if we can really get in there. So this side will reflect a lot of light. The other sides are pretty dull. And you'll see that especially with the potassium here. I'm going to go ahead and give this kind of a half cut. So for the potassium, this is the side that's freshly cut, and you can see the dullness to the other sides compared to that one. So I'm going to go ahead and take those three, and I'm going to add them to water, and we can look at the kind of reactivity of those 3 alkali metals with water. So here I'm going to take the lithium, add that to the water. It's going to generate hydrogen gas and lithium hydroxide. So you're going to see a pink color develop here, and then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off of there. Maybe a little bit of liquid water. But it's not as reactive as, say, sodium, so I'm going to put sodium into the next one. And sodium is actually probably going to ignite. So you'll see some orange flame perhaps, or some sparks, or some shrapnel. And then the last one, I'm going to go ahead and put my 2 pieces of potassium in that I've cut in half. So this is less potassium than the other 2 in terms of amount. You'll find that the reactivity is a little bit greater. Now that potassium there was quite reactive there, but the sodium sometimes will allow hydrogen gas to build up. In this case, it's not igniting. But we can try adding another piece here. We can hope that that's going to go ahead and actually send off some shrapnel and some flame. All 3 produce hydrogen gas. All 3 produce hydroxides. There's your alkali metals. Next, we're going to go ahead and do the rubidium and cesium.
Okay, so yeah, if you go ahead and do the same experiment with rubidium and cesium, that is going to be really, really dangerous. And usually the scientists, they keep distance. They use big long rods instead of their hands directly. So did you see how it caught fire? So yeah, you need to wear goggles, gloves, and everything, and you need to keep your distance. Okay, yes, Aisha, you have any question?
When sodium is cut, why doesn't it react with the oxygen?
Yeah, it does. It does. So that's why the surface was black, because of sodium oxide. It had already reacted. But yes, that reaction is not as explosive as with water. Okay, you won't see any, fire getting caught, but yes, it had already reacted, and that is why the surface was dull black. Okay, another question real quick, last. Why do you think we look at the reaction with water and air only for, comparing their reactivity? Why are these 2 reactions most commonly studied? It's a common sense question. Yes, Aisha, I see your hand raised.
The others would be way too reactive.
The reason, simple, basic reason is that they are most commonly available, first of all, and this is what commonly in the environment, in the atmosphere, we come across. So we need to know, because there's always humidity, moisture in the air, and there is, of course, oxygen in the air. So we want to know how these metals will behave if we expose them to the air, when we are transporting them, or if you want to make ships out of them, or if you want to make buildings out of them. How will they react with the atmosphere? Okay, how will they react with water, and how will they react with oxygen? We are interested in that. Okay, so that is one basic reason. So I roughly covered group 1 and group 2. Okay, and so yeah, this is a big topic. Is this whole chapter coming in the exam?
Yes, Miss, chapter 6 and 8.
Yes, Miss.